So in our last video segment, we ended with this slide. We have these two equations at the bottom here, and what do these equations tell us? Well, Gauss's law is where we started in the first part of 802, and one of the consequences of Gauss's law is that it's possible to have surfaces inside of which there's an isolated charge. You do an integral over some closed surface, and the integral of E dot dA over that surface tells you how much charge there is inside the surface. And this relates to the fact that if I have a dipole, which has total charge 0, I can pull the plus and the minus charge apart and separate them into two isolated charges, one positive and one negative, which we now realize we could call electric monopoles, although that's not what they're conventionally called. Now, for magnets, things are different. We have the magnetic Gauss's law here, which has a 0 on the right-hand side instead of a Q, and that equation tells us, that 0 on the right-hand side tells us that there are no monopoles. That equation says that for any closed surface, if you do the integral of B dot dA, you just get 0. That means there cannot be a monopole inside. Another way of saying what this equation tells us is that magnetic field lines never end. There are no isolated point magnetic charges on which a magnetic field line can end. And so all of this implies the difference between an electric dipole and a magnetic dipole that we talked about last time. With an electric dipole, if I split the plus and the minus, because the field inside the dipole is pointing back this way, if I separate the plus and the minus, I'll end up with two isolated charges. On the other hand, if I break a magnet, because the magnetic field in the magnet is pointing this way, and that's related to the fact that magnetic field lines never end, so the field lines have to curl through the magnet like this. If I break a magnet in two, I get two new magnets, two new dipole magnets. I do not get an isolated monopole. So these two equations, this is a natural punctuation point, pause point in 802. We are now halfway there in terms of building up the fundamentals of electricity and magnetism, the fundamental laws that I talked about at the very beginning of 802. We have two out of Maxwell's four equations. This is Gauss's law, and this is the magnetic analog of Gauss's law with this key difference of the 0 on the right-hand side. And so we have two out of the four Maxwell's equations. We have the Lorentz force law, which tells us what electric and magnetic fields do to charges. An electric field exerts a force on a charge. A magnetic field exerts a force on a charge only if that charge is moving, and then the force is perpendicular to V and B. So we have two of Maxwell's equations. We have the force law. And what's left in terms of building up the fundamentals are these other two equations here. And we are very soon going to start describing this equation with the first term on the right-hand side, with this I term on the right-hand side. And then in the third part of 802, we'll complete our construction of the fundamental laws of nature that describe all of electricity and magnetism by getting to this law, which is called Faraday's law, and the second term on the right-hand side of this bottom right equation. So we're about halfway there. We've built a decent chunk of the fundamental underpinnings of how we describe electric and magnetic fields in nature. And we look forward to completing the fundamentals, and then, as we said at the beginning, one of the things that we're going to discover is that from these fundamental equations describing E and B fields, all of a sudden, like magic, light is going to pop out. And that is something you have to look forward to a little bit later.
We now would like to look at another property of current loops, which we're going to refer to as magnetic dipole. So let's suppose that we have a loop of current in a conducting wire. So we have a current I, and accordingly, we're going to draw a unit normal with the right-hand system. Now, this current loop has a characteristic magnetic field, which we've looked at, and I can draw a few field lines, circles around the edge, field coming up, going out like that. So here's the characteristic field lines of a current loop. And what we'd like to introduce is a quantity called the magnetic dipole associated with the current loop. So what we have is we're going to have a vector, and that vector is going to point, it's called mu. Sometimes people write this vector as m. We'll use mu. And the definition of the dipole moment is the current times the cross-sectional area of this plane. So let's make a little plane here, and we'll indicate area A, times the area A, and its direction is given by the right-hand rule. Now, this magnetic field looks very much like the field of a magnet. So if I were to draw a north-south magnet outside the magnet, the field looks similar. Of course, inside the magnet, the field is different because the field lines are moving up. And so a simple bar magnet will also identify as a magnetic moment, mu, with that bar magnet. Now, one of the key things is, why is a current loop where we have moving charges a magnetic dipole, and a bar magnet is also a magnetic dipole? Well, magnetic materials like a ferromagnet consist of atoms in which there may be one free electron in the external shell, and that electron can have two spins, up or down. So it's actually a quantum mechanical particle, but you can think classically that electron is orbiting the atom, that one free electron is like a current loop inside an atom. And so a ferromagnetic material you can think of as a bunch of tiny little atomic current loops. Now, those current loops could be oriented in different directions, but when those current loops line up in domains, they can all add up to give a macroscopic magnetic moment. And in order to understand this in more detail, we'd have to look at the magnetic properties of materials, which we'll not look at the moment. What we're going to just do is look at this simple current loop and consider this our definition for magnetic dipoles. And now we'd like to explore what happens when you put that dipole in fields, in magnetic fields.
So you have seen since high school, maybe even since elementary school, that when you have two bar magnets, if I have a bar magnet here with a north pole and a south pole, and then I have another bar magnet here with a north pole and a south pole, when the two north poles are towards each other, they repel each other. And if it's a north next to a south, they attract each other. You've seen this since high school. We're now learning how to describe it mathematically, but I also want to point out how to understand this the way Faraday would have, with Faraday's intuition of how magnetic field lines behave. Faraday didn't like to use math. He did all the amazing things that he did based on a physical intuition for how magnetic field lines behave, and that physical intuition is now embedded into Maxwell's equations, which came after Faraday. Faraday understood all of this intuitively, and it's really, really valuable to have this intuition. So how does it work? So if we think about the magnetic field lines from two magnets drawn like this, then the magnetic field lines come out of the north poles and go into the south pole. So here's a magnetic field line going around like this, and here's a magnetic field line going around like this, and here's a magnetic field line going around like this, and here's a magnetic field line going around like this. But now we have to start drawing the field lines closer to each other, and so we have field lines that come out like this, and like this, and like this, and like this. And we have field lines that come like this, like this. And Faraday's intuition was that the repulsion between these two magnets comes because you're trying to when you try and push them together, you're trying to squeeze the field lines towards each other. The field lines have tensions that they don't want that. And so Faraday had this very visceral intuition for how magnetic field lines behave. He understood that this was the pattern of magnetic field lines. He didn't have the math, but he had the completely correct understanding. He built it from all the beautiful experiments that he did. He had a completely correct understanding for how the magnetic field lines were shaped. And from the shape of these field lines, he could feel that these magnets had to repel each other. And this was Faraday's intuition. Similarly, how would Faraday have understood the attraction between two magnets with a north next to a south? So I'll leave this one as it was. This one I'll turn around and put the south pole here. So now I can have a magnetic field line that comes out of this north and goes into this south. I can have another one that does this. I can have another one that does this. I have another one that does this. And I'm still going to have field lines that go around like this, come around like this. But the configuration of field lines in the middle here looks quite different than what we had before. And now what Faraday would have said is that field lines have tension. And this, as the field lines the tension of the field lines is trying to scrunch this field down and trying to pull the N and the S together. And again, he had this visceral physical intuition for how magnetic field lines behaved. And everything that Faraday understood in this intuitive way, we now understand mathematically. And what you are doing in 802 is learning how to describe this physics, what magnets do, learning how to describe it mathematically, which is really important. It's important for you to do because it's important for you to do if you want to solve 802 problems and do well on an 802 test. It's also important for you if you want to understand how to build modern technology. So it is, we would say, important for you to understand the math, and that's a big part of what you're learning. But Faraday didn't need the math to understand what happens, and I think it's also really important that you develop your Faraday-style intuition also. I will point out that this, we could have exactly the same discussion about electric field lines. If this was a plus charge and this a plus charge, and let's just kind of ignore for a second the two south poles far away over here. If this was a plus charge and a plus charge, then the electric field lines would have the same shape. So Faraday would have said the same things about why two positive electric charges repel. He would have said the electric field lines are, you're trying to push them against each other, and that's where the repulsion comes from. If he was discussing a plus and a minus, he would have said the same thing, that the tension of the field lines is trying to pull the plus and the minus together. So at this Faraday level, there's great similarity in how you understand electric and magnetic forces. The big difference has to do with the fact that magnets always have other ends, which we will talk about next.